Today we're going to start working on what circuits can do practically. One of the most important circuits that you're going to learn about is adders. Adding two numbers together, because on the hardware level, computers can only understand numbers. Data such as letters and pictures and stuff like that are encoded as numbers in this computer system, so it all boils down to the manipulation of numbers. Adding is the most crucial one of those, because adding, you could do addition, add a negative number, and that's subtraction. Repeated addition is multiplication, and repeated subtraction is division. So adders are a very important circuit to learn about. So you have 2 bits. Start with 2 bits. You to add them together, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. But then you run into the problem of 1 plus 1. In binary, the result is 2, so you would need a second, a 1, 0, so you'd need a second output. The sum would be 0, and the carry would be 1. So your outputs, you would have 2 outputs. Now, you might recognize the 2 columns here as being 2 different functions that we've learned about already. The carry is simply the AND of the 2 inputs. So you would have an AND gate, and recognize the sum. What function would that be? Not OR, XOR. So it's so the circuit would be sum and carry would give you that functional output. So now if you were to implement this with conventional logic, instead of using an XOR gate, you would have And like so. A, B, sum, and carry. So this right here is your XOR gate. And you would have the AND gate for the carry. The NAND implementation is fairly simple. It's very close to just a simple XOR gate, which we know uses less transistors than the conventional implementation. So you have the oops. The XOR gate in the NAND implementation, but you don't need a separate AND gate for the carry because you're already ANDing the A and B inputs here. So all you would need is an inverter to invert the inverted output of this NAND gate here. So this uses 5 gates as opposed to the, 6 gates of the conventional implementation. Yeah. Mm-hmm. Down here? Yeah. Oh, for up here? Yeah. No, this is the sum. This is an XOR gate. And that's the sum. And this is the carry. You just invert the output from this NAND gate. You just invert it for the carry. So you generate the sum and the carry from A and B. Now, this is all well and good for just if you're adding 2 bits together, but most computers add more than 1 bit at a time. So what you have is a full adder. This, by the way, is I'm sorry, I should have specified. This is called a half adder. It is not. It's not the full adding circuitry. you would you don't have anywhere to go with the carry bit. So if we see people drawing their little diagrams, but let me know when you're all done with this. All right. Now the full adder takes into account a carry. It's adding 3 bits. So you have A, B, C in, C out, and sum. So you have 3 inputs. So you'd have 8 possible inputs. So you have 0 plus 0, it'd be 0 in the sum, 0 in the carry out. 0 plus 0 plus 1 be 0, 1. 0, 1, and 0, again 0, 1. And then carry 1, sum 0, back to 0, 1, 1, 0. 1 plus 1 is 1, 0 again. And then 1 plus 1 would be 1 in the sum, 1 in the carry. That's the carry out. That's the second bit of the output. Yeah. So yeah. I mean. So you're at the full combination of 3 bits being added is this combination of outputs with 2 bits being the result. When I connect multiple full adders together, you'll see where the carry in comes into play. So for the full adder, you take a half adder, feed that into another half adder, we'll do this as the carry in, A and B, and then you and Let's put these dots here. Okay. Oh, that's the sum, and that's carry out. All right. So you see that this is one half adder, and this is the other half adder. So that is how you have a carry in your calculations. You carry in the bit from the previous column into the next column, and then you can add 3 bits together. Now the NAND implementation of this is fairly straightforward. Two exclusive OR gates, and then you take the outputs of the first AND gate, NAND gates. I'm sorry, the first NAND gates of the 2 XOR gates, and then NAND those together. And people finish with this diagram. I'll erase it and show you the NAND implementation. Everybody about got it? Basically, this is exclusive ORing the 3 incoming bits together for the sum, because it only it is true if there's an odd number of bits. It's like the even parity generator from the quiz on Friday. And then you have the carry from the 2 half adders, and either or. If there's a carry in either half adder, then you have the carry out. For a NAND implementation, you would have the first exclusive OR gate feeding into the second exclusive OR gate, so you'd have your sum there. And now, to OR two inverted AND gates, or two NAND gates, you would just NAND those. So you have exclusive OR, exclusive OR, and the carry out. It looks like a lot, but when you break it down to its individual components, it is actually a easier implementation than using conventional logic. The nice thing about drawing diagrams is you don't typically have to draw out all the gates and all that sort of stuff for the full adder and the half adder. So the half adder you have a block diagram. Much easier. So you, and the full adder is like so. So when you're dealing with adders and full adders and half adders, a lot of the times you just draw the block diagram and be done with it, and you don't have to worry about drawing all the gates. Unless whatever assignment you're working on calls for you to draw all the gates, in which case you would need to. But we'll see how to link these together in just a few minutes. I still see some folks drawing, so we'll link these together so you could add multiple bit binary numbers together to get a result. I think most people's pens are up, or I got one more here. All right. So with you having these adders to create a what's called a ripple adder, you would have a and then you'd have your carries going into the carry in of the next adder. And if you have, this is for a 4-bit adder, when this result is valid, when this result is valid, the carry out here is valid, and this can calculate S1, and then we'll have carry out here, and let's go ahead and then this one would be valid, then this one would be valid, and then this one would be valid. So it ripples along as the first bits are calculated, the next bits are able to be calculated, and it ripples down the line until you have a completely valid output. But that is a 4-bit adder. I'm sorry? Oh, I'm sorry. You're right. I just, counting to 5 is challenging. No, for an adder, it does not need a CN. There's no bit coming into it. You're just adding A0, B, A1, B2, A2, and A3. There is no bit coming in. So the first one can be a half adder if you're just doing an adder. There is the option to make this a adder subtractor, which would necessitate using a CN and a full adder on the first bit. So how you do that, you would make this a full adder, and that's subtraction. And then let me go ahead and erase these. Now what I'm doing is giving the option of inverting the B number. Now how do you make a B a negative number? How do you make B, if B is coming in a positive number, how do you make it a negative number? And you invert it and add 1. You remember to create a 2's complement negative number? You invert the bits and then add 1. So if you pull your subtraction bit high, and run it through an XOR bit gate for B, if one bit is high on an XOR gate, it inverts whatever's on the other bit, right? We X XOR with 1 equals X prime. I think I remember putting that on the board at some point. So if this is 1 for subtraction, 0 for addition. If you have a 1 in the subtraction bit, it adds 1 and it inverts the number you're trying to subtract. So that makes an adder and adder-subtractor. I'm curious about something. Just invert the B bits and add 1 to the carry-in of the first adder. Makes it subtraction. All right. Any questions about adders and subtractors? Pretty well understand it? All right. Don't have time to get into multipliers, but we can wrap things up here. We'll get into multipliers on the next session. Have a wonderful day.